Today I'm going to talk about, so let me put in full screen. Okay, so I'm going to talk about, it's a bit different. I mean, I have to say that it's quite different from stochastic partial differential equation, because in this talk, I'm going to treat kind of fundamental problem in the rough path theory. And but in the next step, maybe we can apply to SPDEs or even singular SPDEs. Okay, so first, this is a joint work with Professor Francisco Rousseau from Institut Polytechnique Paris. And so it's a work in progress. So I just want to discuss with you the preliminary version of this of our results. So since there are not so many specialists in rough path theory, and there are some specialists, some of them, but okay, I decided to this morning. I decided to write a few words about what is rough path is about. Okay, so let me start with a function x. Capital X is just a gamma-Hilbert continuous function with regularity gamma between 0 and 1. 1 is obviously the boundary variation Lipschitz case. So if you consider, you also take y as an alpha Hilbert continuous function. I'm sorry, this is a typo. Continuous function such that alpha plus gamma is bigger than 1. So we know since Young in 1936 that this Riemann sum exists, and this generalized the usual Lebesgue-Stieltjes integral. Okay, so beyond the constraint alpha plus gamma bigger than 1, some approaches have been developed by probability community. Most of the people working in this area works in probability community. So Ito, many people, starting from Ito, completely independent from Young. I mean, that time there was no connection with Young integral. Malievan calculus, many authors, and Rousseau Valois, also they contribute a lot to this to this object, the integrals beyond the boundary variation case. So a breakthrough came with Terry Lyons, with the advent, with the invention of rough path theory, and in case y and x has lower regularity. Okay, so I will start with just I will start with the basics for non-specialists. I'm sorry for people who already know this theory. But so if y admits a Taylor-like local expansion, so why Taylor-like Taylor local expansion? Because so if you assume that the increments of the function is a linear function of the increments of your driving noise, so you may think capital X as the driving noise of your system, which is given. Y prime is a Hilbert continuous function with regularity gamma, with the same regularity as the driving noise. And then, so C1 gamma is the usual vector space of Hilbert continuous functions, one parameter. And the remainder term here, Ry, is a two-parameter, it's a function of two variables, and it has C2 gamma regularity. When gamma, let's say, is between 1/3 and 1/2. Okay, so if you assume that x has this kind of regularity, then you are in the good framework, because in this case, rough path theory tells you that if you are able to lift x, the driving noise, into two variable function, two parameter function, satisfying this kind of regularity condition, and also chain relation. So this is algebraic constraint of the rough path theory. Then under these conditions, A, B, and 1, then we do have convergence of the Riemann sum, okay? And then we call this object as the rough path integral. So here, x and double x is called the so-called gamma geometric rough path associated with your driving noise. Okay, so what is the connection with probability theory? So far, this theory is completely deterministic. I have to say that it's completely deterministic. But the motivation behind rough path, it's really probabilistic. Let's consider x and y stochastic process. What does it mean, stochastic process? Means that you have two functions which depends on your, there is a probability space on the top of x and y, omega, f, and p. P is the probability measure. And then omega, for me, it's a random element. And if you assume that x and y satisfies, this pair satisfies assumption A, B, and 1 for almost all omega, then if you apply rough path, as long as you are able to lift your driving noise into what I discussed before, the so-called geometric rough path, then this integral, it makes sense. It's well defined for almost all omega. Okay? So there are many things to discuss about, many applications, many things to discuss about rough path. I just want to say that this integral complements Ito theory of stochastic integration under pathwise Hilbert regularity conditions. And more importantly, it extends to a large class of driving noise beyond semi-martingales. The semi-martingale is a typical type of process in stochastic analysis that people do applications in many kinds of engineering, in biology, in physics, and so on. So the important fact here is the fact that under Hilbert regularity on the couple y and y prime, so this rough path integral, it coincides with Ito-Stratonovich integral. Okay, so the left-hand side of equation 3 is the rough path integral. So then you can interpret, as I said before, omega n by omega, and you fix on omega the random element of y, capital Y, and you fix an element, a random element of your rough path. Then you do have convergence on the left-hand side of equation 3. And it turns out that this object here, it coincides with the stochastic integral. The probabilists, they know that you are not able to fix omega, but with the invention of rough path theory, then you can prove that there is, for almost all omega, there is equality here of these two integrals. So in case x is a continuous semi-martingale. So an important fact is, I just want to recall that Ito theory does not need any type of Hilbert regularity, but only integrability condition on a type of tangent space of the derivative of y, plus some measurability conditions with respect to the driving noise. Okay, so for people who are familiar with Malevin calculus, the tangent space here is the Cameron-Martin space, and measurability is the adaptive with respect to the driving noise. Okay, so rough path, it's a huge, now today it's a huge research field with many applications with stochastic differential equations, and more recently to SPDEs, and more specifically to singular SPDEs that I think that Dirk was going to talk about later on. I just want to say that there is some higher dimensional extension of the rough path, and this is the extension was due to Martin Heyer, and very fashionable today, regularity structure applied to singular SPDEs. Okay, so in this talk, so the goal of this talk is to give a closer look on this object here. On the left-hand side is the rough path integral. And I want to investigate the connection with rough path integral with respect to stochastic integrals in the classical sense, beyond the case when the driving noise is the classical semi-martingale. Let's say it's a Gaussian process with very low path regularity. Okay. So I want to study this kind of connection. And if there is a connection, this is the first question, is if there is a connection, how it behaves, these two integrals. Okay, so based on this first words about rough paths, let me present precisely the question that I want to tackle in this talk. So from now on, a capital X is a stochastic process, or in other words, it's a random process, right? With this kind of regularity, 1/3, gamma regularity, 1/3 and 1/2, and I keep it with the second order process that I just mentioned before, and in the sense that this couple is a geometric rough path. So as I said before, rough path theory, you can define this convergent for almost surely, as long as the increments of y, as I explained before, is suitable. The increments are kind of there is a kind of regularity with respect to the driving noise in a linear way, and y prime, it's called the Gubinelli derivative. So I just want to mention that y prime is not unique, and the rough path integral heavily depends on your choice of double x and y prime. So more importantly, as long as you are able to lift x into your rough path, then there is no probability measure. I mean, the underlying probability measure does not play any role in this convergence as long as you are able to lift your driving noise into rough path, geometric rough path object. Okay, so because of this, roughly speaking, rough path is really geometric calculus in the sense that when you consider the change of variables formula, f of x, when x is keep it with a rough path, geometric rough path, then you get this usual change of variable formula, just like in the classical calculus. In contrast, I just want to recall that in contrast, stochastic calculus, it's not like this. We have some correction term when you plug a smooth function applied to a stochastic process, okay? But this is a strong contrast, as I said, when you consider the classical stochastic calculus when x is a semi-martingale, and also Malievan calculus. So probability measure plays a role in those integrals. So for instance, like Christian said this morning, so if x and y are two continuous semi-martingales, then there exists a correction term. We call this quadratic variation, x against y, where you can transform Ito integral in terms of Stratonovich plus some correction term here. Okay, so there is a connection between Ito and Stratonovich, and this is the correction formula between these two integrals. So beyond semi-martingales, it is known that if you consider x a Gaussian process, and y is that the derivative of f applied to your driving noise x, then what you get is, so this the first expression here, it's just the fact that the rough path, as I said before, is a geometric calculus, so the usual chain of variables formula, and at the same time, if you use Malievan calculus, then you can prove that this integral here is actually the Skorohod integral. So the delta here denotes the Skorohod integral, plus this Young integral. Sorry, not Young. In this case, it's even simpler. It's Lebesgue-Stutz, because R here is assumed to be a finite variation, which is the variance of your process. But the important fact here is that you can write it down, rough path integral in terms of Skorohod plus some remainder term, which depends on the covariance structure of your Gaussian process. Okay, so in spite of many rough path theory numerous achievements, sometimes people, they feel a little bit uncomfortable with the fact that there are some high order correction terms that, of course, that if you insist in working omega by omega pathwise way, then it's impossible to get rid of these correction terms. But it is important to know under which conditions do we have, can we neglect, in some sense, the high order correction term if you make use of the probability measure. Okay, this kind of question is also important for numerical analysis, because the presence of the rough path approximation, Levy area, the so-called Levy area, integrated integrals, it's really difficult to implement numerically. So as I said, ideally we would like to take limits on simple Riemann sums, and pathwise this is impossible, omega by omega. But what happens if we make use of the underlying probability measure? So, and then is there any connection with rough path integration and Skorohod integral in Malevin calculus? So this is the motivation. More precisely, so first of all, I want to assume the existence of the rough path integral in the sense of Gubinelli. The first question that we want to address is it possible to approximate the rough path integral in terms of usual Riemann sums, for instance, if you make use of the probability measure? Or more precisely, want to avoid the usual high order correction term, which comes from the Levy area on this double X here. So the question 2 is how close is rough path integral from the Skorohod integral if Y has some regularity condition in the sense of Malevin calculus? Okay, so this is the second question that we want to address. Now, so in this talk we're going to address these two questions. But actually, our motivation for this paper is actually the following: to address the following question. So, if you consider Y and Y prime a couple of controlled processes in the classical sense of, not classical, in this sense, it's a kind of local expansion for some R orthogonal to X. So this is very formal at this point. So the question is the following: is it possible to get rid of the pathwise Hilbert regularity condition on the couple and to formulate a weaker condition in the Malevin calculus in such a way that this expression here converges in probability? So pay attention that I'm not saying convert path omega by omega, but the probability measure here is very important for us to address this question. Okay, so in this talk, I'm going to discuss about these two questions. So if I have time, we can discuss about the question 3. So let me give you some references about these questions. Question 2, Hu, Jolis, and Tandel, they have obtained this correction formula here in the gradient system case, when Y is the gradient of a smooth function. And in a driving noise should satisfy this regularity condition here. So, for instance, fractional Brownian motion does not satisfy this condition, but this the first paper addressing this question. So you see there is a correction term here, which comes from the fact that x is Gaussian and the rough path integral is not equal to Skorohod, but you can compute the correction term here. So in the same kind of literature around question 2, Cass and Lin, very recently, they proved that if y is a solution of a rough differential equation, this equation here, and driven by a smooth coefficient v, then the rough path integral is the Skorohod integral plus some remainder term. This remainder term here, it depends on the derivative of your solution. So this is the Jacobian of the rough differential equation, of the derivative of this solution here with respect to the initial condition. And this double integral here, it's a two-dimensional Young integral. When R is the covariance of the Gaussian process. And this one-dimensional integral here is the variance, as I introduced it before. Okay, around question 1, some authors consider this problem, let's say old papers in some sense, and but so far this works. There's no connection with rough path integrals. It's this kind of approximation here. It's really a Stratonovich type approximation, and this integral here is Stratonovich integral. You can also think in terms of Rousseau-Valois integral. Essentially, it's the same as the Riemann-Sum approximation, but with some kind of regularization by using Riemann integral. Okay, very recently, Tandel also proved that, okay, so in the rough path case, provided that y and y prime is a controlled process in the classical case, in the classical sense, then you can get rid of this high order approximation here. Okay. Okay, so our contributions are the following. We characterize the rough path integrals as Stratonovich type integrals in the sense of Rousseau and Valois, and the classical Hilbert type regularity in the sense of rough paths. And y prime, it satisfies some regularity in the sense of Malievan calculus, but very weak regularity. And more importantly, we show that the rough path connection between rough path integral and Skorohod integral in the very general case, and we identified the correction in terms of a trace term specified in terms of the Malievan derivative of y. Okay. So this our result extends the recent result of Cass and Lin for a harder general class of controlled process, much beyond the rough differential equations. Okay, so the main message, before I enter into details, the main message of our theorems is the fact that the correction between rough path and Skorohod integrals is precisely given by this object here. And y and y prime, it's a controlled process in the sense of rough paths. If we assume that it admits very weak regularity in the sense of Malievan calculus. So if this is the case, then this formula here holds true. Okay. So so now I want to give the details of the framework. So first of all, I just want to give the basic condition of our underlying Gaussian process. So this is the expectation of of my process. So I will call right the covariance of the process. So a priori, R is only continuous. So when I write this second order derivative, it's always interpreted in the sense of Schwarz distributions. Okay, and for simplicity, we work on the real line, on the positive real line, rather than 0 capital T. But capital T is fixed, so my process always will be stopped after time capital T. So the main idea is to explore the regularity of the covariance structure of the diagonal. In typical case, the singularity comes from the diagonal on the Euclidean space, on R2. So this is the idea. So we develop kind of Malevin calculus to deal with this kind of singularity. Okay, so the technical assumption here, I don't want to extend too much about this discussion here, but I just want to say that the most important assumption that we need is the fact that the second order derivative in the sense of distribution is actually a regular distribution and is a sigma finite measure move. Okay, this is very important. Okay, so it's some technical assumptions in the sense of the variance. And also we need some growth conditions in the respect to when you consider the second order derivative on 0 capital T product of the diagonal. Okay, so we need this kind of regularity. And of course, that X had to satisfy some gamma Hilbert continuous regularity with this kind of on this range. Okay, so the first example it's a classical one in the literature on rough paths. It's a fraction Brownian motion. So the fraction Brownian motion has this kind of covariance structure here. And so the most important object for us, I just want to bring attention for the second order derivative. This is the formula. So fraction Brownian motion, it's a classical case, classical example of rough path theory, and but it has stationary increments in the sense that in the probability sense. Okay. Beyond the stationary increments, then one example in our framework, it's a bifractional Brownian motion. It's a generalization of fraction Brownian motion, but it does not have stationary increments, but it satisfies some nice conditions. For instance, gamma Hilbert regularity. So bifractional Brownian has 2 exponents here. So this is the covariance structure of the bifractional Brownian motion. Okay. Okay, so with this driving noise at hand structure, the idea is to investigate the Gaussian space, the underlying Gaussian space for a given Gaussian process X. Of course, there are many alternatives dealing with Malevin calculus because the probability measure here is really a Gaussian measure, so you can copy, let's say, Nuala's book and whatever. But we need to reformulate a little bit, quite a bit, let's say. I have to say that the formulas of Malevin calculus, because our analysis is based on the derivative of second order derivative of R rather than R itself. People who are familiar with Malevin calculus, they know that if R has a reasonable good covariance structure, then you can develop Malevin calculus and so on. But here, we need to take advantage of the second order derivative, okay? And also, we're going to discuss this in a minute. We want to express the Levy area, the rough path written in terms of the Skorohodin integral. So this is very important for us. to prove the main theorem, to find the connection with rough path and Skorohod integral in a very large class of examples and problems. Okay, so the idea is we introduce some L tilde R. It's a basic space, space where functions, RD value functions, where this number here is finite. So mu is the measure associated with the second order derivative. Recall that the second order derivative, it's considered in the sense of distributions, but we assume that it's a regular distribution, and so it is representatives of a measure. So this is the total variation measure of mu, and this is the total variation measure of R when you integrate only with respect to the first variable. Okay, so we consider a set of smooth functions, C1, with a compact support. And we define what we, later on, will be the classical Paley-Wiener linear mapping in this Malevin calculus framework. So we consider the LRRD as the closure of the set of smooth functions, a C1 function with compact support with respect to this norm. And then, because of that, this relation, this is our definition of the kind of stochastic integral when f is smooth. Okay, so in this case, you can do this kind of change of variables. And then, for obvious reasons, I, it's for us is a Paley-Wiener integral, and LR is the reproducing kernel Hilbert space in this Malevin calculus framework. Okay, so then you can always consider the Sobolev space, Watanabe Sobolev space in the sense of Malevin calculus. I don't want to enter into details because this is classical notation. And the Skorohod integral I will define as the action of the adjoint of the Malevin derivative applied to this to a process U times the indicator function. Okay, so it will be important for us to lift the driving noise into the rough path in such a way that the Levy area, the second order process, it's really a Skorohod integral. So this is the first step, and I would just want to recall here the definition of Rousseau-Valois Stratonovich integral. So this is the definition. And okay, so based on this definition of stochastic integration, then one can prove that it's possible to consider the Levy area written in terms of Stratonovich integral in the sense of Rousseau-Valois, and it satisfies this the chain relation, and it's also actually a geometric rough path, where S here denotes the symmetric part of double X. Okay, so in order to state the first result, I need to introduce some spaces. WP gamma is the set of functions where two variables functions where this integral here is finite. So var theta here is the product of these two indicator function. And also I need to define the planar increments of a two variables function. And I give a rectangle I, product of the Cartesian product of these two intervals. Okay, so for my, I just want to recall the definition of C alpha 2 to denote that is the Hilbert regularity on the two variables function. And we also consider the tensor product of the Hilbert space LR. Okay, so proposition 1, it tells you that one can construct a Levy area in terms of the Skorohod integral when I is different from J. I just want to recall that X is double X here is a matrix, okay? And in the diagonal, we have the Skorohod plus some remainder term here, which can be explicitly computed. So under some regularity conditions in the covariance structure of your Gaussian process, then this is the additional regularity, then double X actually belongs to C2 gamma almost surely. Okay, so this proposition is the first step to solve our three questions, right? Because remember that we need in the question 1 and question 2, we need especially question 2, we need the connection. We want to investigate the connection of rough path with Skorohod integral. Okay. Okay. So I just want to say that assumption 7, it's really about the covariance structure of your driving Gaussian process. You can rewrite this condition here in terms of this sum of integrals, where the covariance structure of your Gaussian process really appears explicitly in this condition here. Var theta, this has to be finite. Sorry, not finite, but it should belong to this space here. Okay. Okay. The first examples, we have many examples, but I just want to show you the classical cases where X is the bifraction Brownian motion. So if you want, in the simpler case, X can be a fraction Brownian motion between 1/3 and 1/2. Okay, I think I have 10 minutes. Now I want to state our first theorem, main result, our first main result. I will recall that the notation dx is the set of all controlled process in the sense of rough paths. And the remainder term here, it's satisfies this condition, the classical regularity condition. So the first lemma in this direction of proving our first result, a major result, is to check that actually equation 8, this convergence, this object here converges to the rough path integral. This is not surprising, but it's some work has to do. But I mean, the fundamental tool for convergence 8, it's really Sewin lemma. Okay. Okay, so in order to address question 1 more precisely, remember that our second order derivative, the covariance structure, it has to be dominated by two functions. One of the functions is phi, and we assume that phi has some kind of nice regularity in the Hilbert type regularity plus some integrability conditions. Okay, it's a technical condition that it satisfies many examples. And okay, so again, I will recall the definition of Stratonovich integral. And our first theorem is the following. So consider X a Gaussian process satisfying the technical condition A to EA, and assume that we are in the rough path case. Y and Y prime is a controlled process in the sense of Gubinelli. So in addition, we assume that Y prime satisfies some Malievan calculus regularity conditions, equation 10. and there exists p bigger than 2 where this integrability condition holds true. Okay, remember that the d is the Malevin derivative of y prime. And then we do have equality between rough path and Stratonovich integral. Okay. Okay, so in order to address question 2, so we need an additional assumption, again in the sense of Malevin calculus. Technical assumptions, so yt is a continuous and bounded function, and we need some kind of regularity of the Malevin derivative at the origin. Okay. Okay, so we need to compute correction terms if they exist. And then I consider y as a process. And well, I assume that dy exists in the sense of Malevin calculus. And I will define tr dy is just this trace term, let's say, of, specified in terms of the Malevin derivative. And R is our Hilbert space, in the reproducing kind of Hilbert space in the Malevin calculus sense. So this conversion here takes place in probability, because this is the definition. So our second theorem, it really gives you the full answer of my second question. If you consider a rough path x, a Gaussian rough path, in our case, constructed in our framework. So if you consider y and y prime control the process in the sense of rough path, and if you assume that y prime satisfies some additional regularity conditions, okay, in the sense of Malevin calculus, then you can write the rough path integral as a Skorohod integral plus some trace term here, specified in terms of the Malevin derivatives. Okay. So our theory number 3, it gives a more refined description of the term, the trace term. So if you assume, in addition to the theorem 2, that the expectation of the Malevin derivative of y, considered as a two-parameter function, it's on the 1 over gamma variation, two-dimensional variation, is finite, then actually the trace term here, it can be computed in terms of the trace of the matrix, Malevin derivative matrix of y prime. Sorry, not the Malevin derivative, y prime. And the Malevin derivative matrix appears here on the second component of the correction term. All right. So let me give a couple of examples. The simplest example is when you consider f C2 function with bounded derivatives. In this case, rough path integral, it coincides with Stratonovich integral. Example 2, if you consider y as a rough differential equation, we also have coincidence of these two integrals. Rough path integral is actually a Stratonovich integral, and in this case, no need for correction terms, high order correction terms in terms of Levy area. Okay, so this is the proof. I think I don't have time to discuss the proof of this example. Okay, so example 3, it's a very didactic example. Y is gx. Again, g is a C2 function with bounded derivatives. And the rough path integral is actually the Skorohod plus remainder term here. dr is the Young integral. A more sophisticated example, it's when you consider y as a solution of a rough differential equation. And so in this case, we can compute the trace term here in a very detailed form, specified in terms of the covariance covariance of the Gaussian process. I just want to remind that G is the Jacobian of Y, so this is the inverse. And dr, double R, this is the two-dimensional Young integral. Okay, so I think that I don't have much time to discuss about the idea of the proof. So I think that I finish here. Thank you very much for your attention.